Verilog coding is used at the very first stage of ASIC design. Writing a Verilog module requires multiple sub-concepts of Verilog to learn in vivid detail. However, you can start learning the entire thing from a bird's eye view. In today's episode, we will give a kickstart to your first Verilog code. Stay tuned, stay focused.
Hey folks, welcome back. In today's episode, we will be discussing the below points. Introduction to Verilog HDL, V-Curve of Verilog design. We'll explain the components of the V-curve as well as why this is a V-curve, means the shape of V. We'll explain that also. HDL compiler versus synthesis compiler. So in VLSI, there are two types of compiler, very closely spaced. We'll talk about them. C language versus Verilog. You will find a lot of similarity with the C language. Hence, we would differentiate the C language versus Verilog so that your concept is very much clear about the Verilog with respect to the C language, which you might have learned already. Next, we will point out the comments in Verilog which are very important of any language. Next, we will go through our typical Verilog module and we will also go through corresponding Testbench to test that Verilog module, and both are examples, that means explicit Verilog code. Next, we will talk about the bird's eye view of any typical Verilog module. This helps you to create a snapshot what are the components that should be there inside a Verilog code. Next, we will summarize our entire discussion. So that's the menu for today. Without any further delay, let's begin. Introduction to Verilog HDL. Verilog and VHDL are the two most common hardware description language, that is HDL, used by beginners in integrated circuit design. So here is a typo, it should be integrated circuit design. HDL syntax and semantics allow the design or sub-design or components to be simulated and corrected during the circuit realization and simulation. Designs described through Verilog or VHDL are technology independent, easy to code and debug. However, in actual practice in the Verilog, we transform this code for a technology dependent synthesizable netlist, and that we will talk later. As HDL, Verilog can be used to describe designs at 4 levels of abstraction. So these are very important. Please pay attention to these 4 points. First, algorithmic level, much like the C code with if, case, loop, etc. Next, the register transfer level, often abbreviated as RTL, uses registers connected by Boolean equations. Gate level, interconnected format of AND, NOR, etc. The basic logic gates. Switch level. The switches are MOS transistor inside the gate. The language also contain constructs. Those are used to control the input and output of a simulation. So from here you can summarize that Verilog is a very well equipped hardware description language that not only describes a digital circuit used for ASIC design, but also it has the necessary components to simulate the behavior of a digital circuit written in the Verilog. We need a simulator, however, to process these codes. We'll later discuss about the paid and free Verilog simulators. So that's all with this particular slide. Let's move on to the next slide. V-Curve of VLSI design. Now this is a very important slide. Please pay very good attention. I don't expect that at the very first go you will understand this. However, this is the architecture that is used in most of the VLSI designs. How a design is realized from the thought level up to the actual silicon. So this curve is a theoretical curve. However, this curve is followed in the practical ASIC design. So let us start with the first step. First, we list out the system requirement. That means whatever chip we are designing, what are the requirements, what should be their input, output, and whatever like the truth table and all. Next, we design the system. At this stage, our design begins. Now, if we dive further down, we see the design subsystem. That means our entire system, a chip, is further divided into smaller blocks of individual design, which are very much independent in performance and functionality. Next, we design components. So for any subsystem to get realized, if we break it further down, we have to design individual circuit components like maybe gate, AND gate, OR gate, etc. Now you might say that the logic is there already. What we have to do? However, the logic is there, but in terms of the Verilog code or synthesizable netlist or the physical layout, you have to design them. So this is the design components. So you can understand this is the very much broader perspective of the chip design. It is not very much specific to the Verilog only, but rather it expands for the entire VLSI design. This slide has its importance. That's why I have kept at the very beginning episode of Verilog, so that you have the impression of this slide and you carry out this slide throughout your entire VLSI journey. At the next stage, a designer realizes the components using simulator, codes, etc. etc. Next, build and check components. So at left, you can see that the design components is here. Once the components are realized, it is build and check for it functionality, connectivity, errors, everything. Next, once the components are done, we move level up to the subsystem level. We design the subsystem with the help of the components. Next, we finalize the subsystem at this stage. At the next stage, when we do a level up, we build and check the system using different subsystem blocks. So this is a very bigger block of design. We are approaching towards the finalization of a ASIC design or a chip design. Finally, once all checking etc are done, we get a working system and the chip is ready for tape out. That means all these steps. Now you can imagine that these steps are there. Okay, once we go past one stage, it is done. No, you may have to iterate in between two stages until the two stages are in sync and properly designed. So maybe from design system to design subsystem, you might have a couple of iteration. From design subsystem to design components, you might have a couple of iteration. From design components to the realized component, you might have couple of iterations. In the similar way, any two stages can have different level of iterations based on the fine tuning, based on the target design, based on the target functionality, based on the put out of any error that is coming. So all these things will be there. It is very much practical to have multiple iteration. That means you are not perfect at the first go of any stage. That might happen in some one exceptional cases, but in real cases, you will iterate through two different adjacent or neighboring stages multiple times. So this is the V-curve of the VLSI design, and the significance is that whenever we start to write a VLSI code, you might think, where are we? This is the entire big curve. Where we are? So let me bring my mouse. So if you are inside a VLSI company who makes chips, right, you might find yourself at the first go. If you are a beginner, right, you might design components first, and the senior folks who are much more senior to you might design a subsystem, and people senior to them might design a system. So these are very parallel. So whoever designing are also checking. So that means you are designing components and you are checking components. As a beginner, you might start with these three parts, and as you grow older in the VLSI company and you get more experience, so you do a level up. The things level up, you level up. So this is the kind of method that is followed in a typical VLSI company. So we are done with this particular slide, and I have shared whatever needed to be shared in this particular slide. Let's move on to the next slide. HDL compiler versus synthesis compiler. Why I kept this thing? Because once you enter into the VLSI industry, you might hear two names. One is the design compiler, it is from Synopsys. Another one is the RC, I think it's from Cadence, so RTL compiler. So these things are somewhere used in the synthesis part. So whatever you are learning with the free tool, maybe as a student right now, you might get confused that, okay, what is the difference? To make you understand the difference and you don't get a jerk once you enter the VLSI arena, I have kept this very simple, short and sweet difference of these two compilers. One is the HDL compiler that you can start using right now with the free versions or the free and open source versions. And once you enter into the VLSI arena in a company, right, there you will get the paid versions, that is synthesis compiler. So these are different things and they are for different purposes. Here, let me demonstrate. So here is your Verilog description, that is a .v file, and it passes through a HDL compiler that you can readily avail as from the archives of the free and open source tools. And this is a translated design. Now we have the translated design. At the next stage, this can be passed through the synthesis compiler. Here I named the DC from Synopsys and RC from Cadence, right? So these can be used at this stage to produced with the help of the ASIC PDK or DK library and the standard cell library, whatever there. Generally, these comes both together, the PDK and the DK. So I have a episode in my channel in the VLSI FAQ about the PDK and DK. Please go ahead, deep dive inside that episode. You can find in the VLSI FAQ playlist this particular episode. There I have explained what is PDK and DK in detail. So please watch that episode. Now let me come back to the point. Once this is integrated with the synthesis compiler, the translated design can be further translated in technology specific synthesized netlist. So this is the difference. The output of the HDL compiler that you can readily do with a free and open source version is not technology dependent. That means it is not from maybe TSMC 90 nanometer technology. It is not from that. So it is technology independent. So that can be used with TSMC 90 nanometer or UMC 90 nanometer. So like that, whatever the foundry, it is independent. Now at the next stage, once you add the PDK and DK in the synthesis compiler, right? So there you add the technology data, and the next level of realization is the technology specific synthesized netlist. So this is the difference between the HDL compiler and the synthesis compiler. So here the short and sweet difference is explained to you. Hope you have grasped the meaning. And with that note, let's move on to the next slide. C language versus Verilog. Generally in colleges, you learn your first programming language as a C language. Now, once you are exposed to the Verilog, you will find a lot of similarity in between the two. And the immediate pitfall for you, you start to correlate both of them. Stop doing that because these two are not same. The reasons are, because Verilog is a HDL, so it is for to defining a hardware. Verilog code intended to be synthesized into actual hardware, actual chip, that is actual IC. As a programming language, C is everything to be converted into executable hex file, which is to be loaded in your RAM while executing the program. So this is the fundamental difference of the Verilog code and the C code. Now let me explain it to further. If you have written A plus B equal to 1 and C plus D equal to 1 back to back in Verilog, then during the simulation both equation will work simultaneously. That means it's a concurrent system. That means everything is simulated with respect to the time. At time t equal to t1, both the equation will get simulated. But in C, everything is sequential and there is no time here. You cannot enter time inside the C language. There are some provisions you can capture the CPU time, or with respect to you can add some delay, but that is not the real transient simulation. So this is not, C cannot do a transient simulation. Whereas in Verilog you can have a transient simulation. That means the simulation where the simulation and the values is changing with respect to time, and time is in x-axis the changes and the values are in y-axis. In C there is no chance of having a time in the x-axis. So this is a fundamental difference of the C language and the Verilog. We are done with the basic difference of C language versus Verilog presented in this slide. So let us move on to the next slide. Comments in Verilog. In any language, the comment is a very important thing. Why? Because whatever you are writing the code, the purpose of the code or the section, whatever means, if other than you, anybody has to read it, they will get help from the comment. Even the code becomes bigger, maybe 10,000 lines of a code in a language, whether it is a hardware description language or it is a programming language. At that time, the comments help you to debug the code with your human eye. Obviously, you will need a debugger or a printf command to debug the actual or final problem. However, initial idea of the debugging, that is helped through the comments in any language. So that is why the comments are very important, and in any language you must first learn what are the comments. In Verilog, there are three forms of comments. This is a multi-line comment. Here you will also find similarity with the C or C++. The double slash is a single line comment. Anything after this double slash is a comment, and within the slash, asterisk and whatever lines are there, and then we end up with the star then slash. This slash star and star slash, whatever contain, even we have a enter pressed or you have a new line character in between, that is a multi-line comment in Verilog, and double slash is a single line comment. Also we have a inline comment, that is not only by the double slash, but that can be placed once a statement has ended with the semicolon. So these are the three forms of a comment that can exist inside a Verilog code. So I have given you the first option. When you start coding, you can put your comments for your own understanding, or you are in a company, your comments will help your colleague to understand the code for a debug. With that note, let's move on to the next slide. Typical module example. Here in this slide, we will give a real-time example of a Verilog module for a digital circuit, and I will point out each and every section, whatever it is called. So this is a kind of visual tour. In next episode, we will simulate these codes in actual simulator. This is the comment. It is your first Verilog program. This is called the heading. Generally, any code has a heading, what the code is, who is the author, and what the section or the division of the VLSI company they are writing the code. All these things will go in the header. So here you can have a multi-line comment or multiple single line comments. Next comes the module, then not get, and we have two ports, that is in and out. So this is the fashion the module is written. Here the module is color in green because this is a Verilog reserved keyword. The not get is not underscore get is written by us, and the in and out is written by us. This is the module declaration. Next, we have input, that is the nature of the input. Here the input, the keyword is in green and it is a reserved keyword for Verilog. Similarly, the nature of the output is output, and it is also a reserved keyword of the Verilog. Together, these two are port declaration. So next we go for assign statement. So this is assign is also a reserved keyword and it is used for any assignment. That means here the output is the inverse of the input. So this is a assignment, and this block is called the functionality declaration. So here with the single here we have defined, and in other cases we have multiple such assignments for the functionality declaration. Next, we have the end module. Here I have used an inline comment of not underscore get. This is a typical practice in VLSI because there will be multiple end module commands and you cannot have a method to know what module is ending. So this way, once you code, it is good practice that you keep a comment, inline comment at the end of the end module of whichever module is ending. So this way, even you have nested modules, then in that case, you might not get lost in a very long code. This is called the module closer. So here are the very short and simple Verilog code of a not get, and we learned here what is a heading, what is a module declaration, what is a port declaration, what is a functionality declaration, and what is a module closure. In next episode, we will simulate in actual Verilog simulator and we'll go through the output. Testbench module example. Now this code, whatever module we have written, we have to test it whether whatever intended functionality, that means it's a not get, right? So that not operation is happening properly. For that we also have to write a testbench. Now testbench is nothing but another module written in Verilog. So this particular module will instantiate the not get and add some test vectors that will help to verify the functionality of the not get here in this particular slide only. In other cases, any test bench will help to verify the functionality of the instantiated module. Here, the first line is a comment, inline comment, test bench. Here it is simple. In actual case, this will be a couple of single line comments or a multi-line comment. Here we define the module with the module keyword, and this is test. Generally, this is a convention that we add a test word so that we can identify later. So this is a test bench module and not a digital get module. Rather than it is a test module. So here goes our module declaration. Next, we have range PLK and where out check. Now these range and where I will discuss about these types in later episodes. Let us learn what are these. So these are data type declaration. That means in Verilog, we can have multiple type of varings and they could be registers, that is reg, or simple var, that is outcheck. I will come to the details later. Initial begin. This is a initial block. We are starting the block, and after this line, whatever we write comes under the initial block. So the begin keywords means we are beginning the initial block. And we write here $dump file abc1.vcd. VCD is value change dump. In the hands-on episode, I'll show you how to open the VCD file in a viewer. Then $dump vars. That means in this file, this particular system command dump file opens a file with the name abc1 and the extension VCD. And in that file, all the changing variables, that is with respect to time, including the time variable, get dumped by the next system command dump vars. Then we have a kind of printf statement, $display, checking output of a NOT gate. So this is a simple printf kind of thing that execute only once. And next we have a recursive printf, that means monitor. Here we use the kind of %d, %b, %b. Then we mention the $time CLK and outcheck. So these are very similar to your C printf command. And the difference is here the $monitor keep on monitoring whenever any of these variable changes, it takes a dump. So this $monitor will give a printout in the screen, and the dump part will go to the dump file. So these are two ways of, one is on the go, you will see the output, and another one is the archiving. So the same data will be printed here in the screen and it will go to the VCD file as a permanent stored result. CLK is equal to 1. We are initiating CLK with 1, that is logic 1. And at time equal to 50, we finish our simulation. So here you can understand the hash 50 is nothing but 50 time unit, and the $finish keyword, which is a reserved keyword, finishes the simulation at this point. In many simulators, the finish can be defined by the simulator. However, in general Verilog code, we already have these directives to finish a simulation. All these $thing, these are reserved system commands which are for controlling a simulation, which are not for a description of a Verilog block, rather for a simulation control commands. All these contribute to the timing block. That means it controls the timing, behavior, output, whatever it is there. Next, we end the initial block with the end command. So this is how the block starts, the initial block starts and ends with the end command. So in this particular slide, we have learned the module declaration of our test bench with respect to our already written module, data type declaration, initial block, timing block. We have not finished yet. In the next slide, we will have the rest of this test module. So let's move on to the next slide. The test bench module example. Always begin. Here, both always and the begin are two reserved keywords. As you know already from the previous slide, the begin means we are beginning any block. And the first line is #5 CLK is equal to inverse of CLK. That means at each and every 5 time units, the clock value will get inverse. That means the clock will toggle. Here we have the end block. So this ends the always block. So the begin is started by the begin keyword and end is mentioned by the end keyword. So this is always block. So this, the difference of the initial and always block is that the initial block is written there, the initiations are done there, and it executes for once only. However, for the $monitor, since it's a system command, it is designed in that way, we just only need to initiate it. The rest of the system, that means the simulator, will take care. For rest of the assignments which need to perform always, which are defined by us and that might be a part of the functionality, are put into the always block. So here you can see the initial and the always block are both are respect to the time. So you can see the stark difference between a C code and a Verilog code. That means here time is very important, and C, the time was found nowhere. Next, here, this comes the most important part of a test bench. Here we instantiate a NOT gate. So first we write the name and we write the instance name is MUT. Here MUT means module under test, and we put the two varings here, the CLK and the outcheck. In next episode, when I simulate, I will tell you what is what and why we are keeping them. However, for now, you can just understand that we connected the CLK and outcheck, which we have defined with range and wire. We connected those things with the actual module. So, but as an instance, not as a library. So this is an instance. The MUT is an instance of the NOT gate. You can name MUT as you like. You can name it instance of NOT gate or like that, or I NOT gate, anything like that. Here I have kept it as a generic name, MUT, that is module under test, because this is a test bench. Next, here this is the module instance, and here we use the end module. Here I have missed out the test bench name to be mentioned here, which is a good practice. So with that we end the module. That means it is the module closure. So in the last two slides, means this slide and the previous slide, we have learned about a test bench module. What are the different parts and subparts, of a test module. So we are done here. Let's move on to the next slide. Now, I have given the explicit example of both module declaration and test module declaration. Now, I will summarize the entire thing here in this particular slide. And this slide will act as a bird's eye view of any typical Verilog module. What you are expecting to write inside a Verilog module. So here goes our details, and in the right hand side, we will have a figure. So first we have the module, then module name. It is mostly philosophically written. It is not the syntactically written. So don't think this is a Verilog code. This is a philosophical bird's eye view. That's why I have kept it. And here we have a pictorial representation of any Verilog module. So let me bring my mouse. Here the entire chip is the module, and here we have subparts or components like this one, this one, this one, this one. And we also have ports which we have declared and connected. And these connections will be either of wire or edge type. We will discuss in further later. We will have the power connection, VDD and ground. So here these functionalities or these blocks, these modules are defined by statements. So you have already seen, now you can correlate with the picture of already discussed module, and you can understand, right? This is the kind of representation of a IC, right? Whenever we put into a breadboard, we can add different voltages to test them out, so to the in and out. So this breadboard where we are putting this chip, this module, acts as a test bench in the Verilog. So we replace the breadboard testing facility with the test module in the Verilog. Here comes our declarations. These are expected to find. You have already come across the example, so you will be easily correlating the things. So these are, I am again emphasizing, these are philosophical presentation. This is not a Verilog code. So whatever comes in under declarations are port declaration, input, output, in out, etc. will be there. Data type declaration, range, where, param, etc. will be there. Task and function declaration. We will later in respective episodes, we will talk about function and task, and we'll also differentiate between task and function. Now the end got color green, but this is not a Verilog keyword, at least here. So don't get confused. Statements are initial block, always block, module instantiation, gate instantiation, UDP instantiation. UDP is user defined protocol, and etc. Continuous assignments in module. So this is a bird's eye view, what you can expect. So whenever you start writing any Verilog code, you can keep a note of this slide with you, that in sequence what you have to write, and you can go back and forth in your book or in this tutorial to go to the respective chapter of that particular command or the code, whatever you are writing. Command, I mean the system command, or code means I write the Verilog syntaxes. This you can keep a handy. This I think I have explained to you with the picture and the text. So let's move on to the next slide. Summary. Now let us summarize whatever we have found in today's episode and also add some more values. Verilog is a hardware description language, HDL, used to model electronic circuits. It is commonly used in the design and verification of digital circuit at the RTL of abstraction. So here in this slide, we are designed a module using NOT gate, and we have used a test module for verification. However, in VLSI, the verification is a vast term and it is a different subject altogether. So I'll not talk about VLSI verification rather than a Verilog verification here. In 2009, the Verilog standard was merged into the System Verilog standard, and since then the Verilog is officially the subset of System Verilog language. Several simulators are there to simulate the circuits written in Verilog. Now, here is the catch. Here I am mentioning the paid and free simulators here. Although in this series I will be using a free or open source or a student version of a paid software. So here are the list of the paid simulators that are used in the actual industry in VLSI. First one is the Incisive Enterprise Simulator. It is from Cadence. Then the VCS. It is from Synopsys. Next we have Model Sim and Questa. It comes from the Mentor Siemens company. Next is the IAC simulator, it from Xilinx. Next we have Quartus 2, which is a Altera and Intel simulator. I think Altera is now the part of Intel, and XSim is a part of Vivado, which is from Xilinx. So these are all paid softwares used in the industry for industrial Verilog simulation. Now we have the couple of names of the free and open source Verilog simulator that you can start using right now. And in the playlist, you will find the installation video of this and installation and usage. So one is the GPL Saver, another one, this is Icarus Verilog. Icarus is very popular because it simulates both Verilog and System Verilog. Next we have a TK-Gate. This is a GUI based HDL simulator, and we have Verilator. So these are couple of names of the paid and free open source Verilog simulator. In next week we will do the simulation of the already shown Verilog module and the test module. So let us keep it secret. Let's wait for the next episode. And I think we are done with the summary. So let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that words in the comment section down below. And bye for today.